Oh hey, I didn't see you there. I was just admiring all these elements.
C-Cube the science dude. C. C-Cube the science dude. Valence electrons rule. C. Heisenberg uncertainty principle. C. SPDF is cool. C-Cube the science dude.
Let's enter the lab where we can talk more about the periodic table. But before we can talk about the modern periodic table, we need to talk about the old periodic table. Let's go! My God, I've got it! It started in 1789 with Antoine Lavoisier. Now they only had about 33 elements at the time, but he did arrange them according to properties. Fast forward about 100 years later. Next came John Newlands in 1864. Now they had more elements by this time, so he arranged his table according to mass. And he noticed trends among the elements, which he made into the law of octaves, where he compared music to science. But the next scientist we'll look at is known as the father of the periodic table. Let's go forward about a couple more years. Mendeleev is known as the father of the modern periodic table. He arranged all the elements in order of increasing mass, and he noticed trends. Now, at this time, they didn't have all the elements, but Mendeleev was so smart that he was able to calculate missing elements that were discovered later. Now, we have one more scientist before we have our modern periodic table. Let's take a look at him.
I'm going to change the world.
And indeed he did. Mostly, instead of ordering his periodic table by increasing mass, ordered it by increasing atomic number. Just like we use today. Isn't that great?
Valence electrons.
Now that we know about how the old periodic table was organized, we can talk about the new periodic table. The new periodic table consists of 7 rows going down and 18 rows going across. The first 2 rows are made of the alkaline metals, which all have 1 valence electron, and the alkaline earth metals, which have 2. These have the s orbital, S for sphere. The next block is the p block, which consists of the nonmetals, the boron group, the carbon group, nitrogen group, the oxygen group, and the halogens, as well as the stable noble gases. All of these have a p orbital for p9. The next part of the periodic table is the d block, and the d block has a clover. The last block that we'll talk about is the F block, consisting of the lanthanides and actinides. The lanthanides and actinides have a flower, or an F orbital. Oh, let's see who that is.
Jailen, I have a periodic table system on and need help.
So the first thing you should know about the periodic table is that it has many trends. Atomic radius, ion radius, ionization energy, and electronegativity. And a lot of these trends are driven by a force called effective nuclear charge. I'm going to have a super cool scientist explain to you what that is. Ms. DeGennaro, what's effective nuclear charge?
Well, let me tell you. Effective nuclear charge is the charge of the nucleus that is effective. So if you look, I have 2 elements here that are in the same group on our periodic table, lithium and sodium. Because they're in the same group in the periodic table, they have the same number of valence electrons. But I drew the Bohr model so that we could demonstrate this. Lithium has 3 protons in its nucleus and 3 electrons on its outside. The effective nuclear charge is the charge of the nucleus that's left over after each of the core electrons shields 1 proton. So each electron shields 1 proton, leaving 1 proton left unshielded. The effective nuclear charge of lithium in this case is 1+. In sodium, there's more electrons and more protons, so there's more shielding. Each electron shields one proton. The end-all effect is that there's one proton left for an effective nuclear charge of 1 plus. Elements in the same column on the periodic table have the same effective nuclear charge.
The first trend we're going to talk about is atomic radius, or the distance from the nucleus to the outermost electrons. The first thing you should know about atomic radius is that going from the top to the bottom of the periodic table, it gets bigger. There are more layers of electrons, and the outermost layers are not as tightly held as they get further away. And as you go from left to right, the atomic radius gets smaller. Now you may be asking, why does it get smaller? I'll tell you. The effective nuclear charge also increases as you go from left to right across the periodic table. The bigger effective nuclear charge holds the electrons much more closely than, say, a smaller effective nuclear charges. But don't just take my word for it. Let's try it.
This magnet is the nucleus of an atom, and that the chalkboard is the valence electron. You can see that the nucleus and the valence electron are very tightly attracted to one another. That nucleus and those valence electrons aren't going anywhere. But as you move down the periodic table, you put more junk in the way between the nucleus and the valence electrons. You put more rings of electrons. The way I demonstrate this is with lunch menus. One lunch menu, there's still a pretty strong attraction. Still good. There's too much in the way. The attraction is not as potent as it should be.
The next trend is ionic radius. Let's talk about that. So an ion is a charged atom, and there are two types of ions, a cation and an anion. A cation is positively charged. It loses an electron, while an anion will gain an electron and become a little bit more negative. Let's take a look at two atoms, lithium and fluorine. Lithium, because it only has one valence electron, will want to lose it. Let's let that lithium lose it. So you can see it lost its outer shell, and now it's slightly smaller. What about this anion? Well, fluorine wants to gain an electron to get in a full outer shell. So let's give it one. But when it gains that electron, it gets slightly bigger.
Wait, why does that happen?
I'll tell you why. You may add an electron, but the effective nuclear charge does not change. When in science, when you have two of the same charges next to each other, they repel each other. So when you have more negative charge than positive charge, the electrons will be repelled, which makes this bigger.
Oh, I see. Zeph drives everything. Can I explain the next trends?
Sure. Where's my lab coat? Okay, Mr. Science Guy, explain ionization energy.
The next trend is ionization energy. Ionization energy is the energy needed to remove an electron. For some elements, like the alkali metals, they have one valence electron that they want to lose. It is very easy for them to lose it. However, the halogens over here have 7 valence electrons, and they want to gain an electron. So it's very hard for them to lose it. That's why fluorine has a higher ionization level than lithium. The final trend is electronegativity. Electronegativity is how much an element wants to hold bonded electrons. If an oxygen atom is bonded with 2 hydrogen atoms,
Isn't that just water?
then oxygen will hog those electrons. Oxygen is so greedy.